Hello everyone. Welcome to a special edition of Coffee and Cloud Native at the Computing on the Edge with Kubernetes conference. My name is Adrian Goins. Usually I have an army of bots who scour the internet every night for news and content related to Kubernetes and Cloud Native, and I come to you live every weekday to share the bits that I find interesting. This show is different, not only because I'm not doing it live, hello, but because I had to do all the scouring myself. When doing research for this talk, someone asked me, what does the edge mean? And I found the question curious, because to me, the edge is a clearly defined boundary. Something running over here is not at the edge, and something running over there is. But as I dug further into all of the projects that are built for the edge, I learned that not only is that boundary in a different place for each person, but its position moves with the objectives of each project. Content delivery networks like Akamai taught us that the edge was as close to the end user as possible. And that definition stood for a long time. But as computing resources have grown in power and also shrunk in size, what you can do at the edge has also changed. An end user and their device is no longer simply a consumer. Devices at the edge are producers of content, and in some cases, they're producers of lots and lots and lots of content. We have to deal with that content locally or regionally, while at the same time, we can't control for every variable. We have to build systems that can think and take action on their own. Take a wind farm as an example of an edge deployment. Wind farms have existed for longer than Kubernetes has, but they're now using cloud-native principles and applications to make decisions, predict failures, and optimize power delivery. Did Kubernetes enable that? No. Containers enabled that. Kubernetes enabled them to use containers better. Containers, in turn, enable them to build applications better. And we can follow this backwards to infinity, even hopping outside of the computing aspect of it. I mean, for example, new materials enable them to harness wind energy better or convert it to electricity with lower loss. And it's actually the enabled them to do X better that's behind the expanding horizon of edge computing. And that's exactly what I want to talk about today. The edge is wherever you need it to be. If you're a retail business, the edge might be a storefront. If you're an oil company, the edge might be a well site. If you're an energy producer, the edge might be anything from an entire wind farm to a single turbine. In finance, it can be an ATM. For others, it could be a vehicle, a camera, an airplane, a mobile device in someone's hand, a streetlight, a 5G tower, a submarine. It's wherever you need it to be. Some of those places are going to be autonomous. Lonely, disconnected outposts that I imagine have cold, bitter winds and long nights, where the internet only comes around every few days with a basket of supplies and then runs off again into the night. Others will have connectivity all of the time, and they may even have resources available to run larger systems with more horsepower. You have to understand your environment and its needs, and you have to experiment. But to do that, you also need to understand what's available. Let's visit some solutions and talk about where they offer value. Starting with infrastructure. KubeEdge is an incubating project within the CNCF. It's built on Kubernetes and offers an infrastructure solution for moving Kubernetes functionality out to edge nodes that it expects to have a reasonable amount of processing power. In KubeEdge parlance, there's the cloud core and the edge core with specialized components running in each. The cloud core contains two controllers and a hub. The hub presents both a WebSocket interface and a quick interface, allowing the edge node to choose between TCP and UDP for communication. It then passes data between the edge node and the controllers. The first controller is called the edge controller, and it acts as a bridge between the Kubernetes API server and the edge core. It synchronizes CRUD events to the edge, updates the API server with data coming back from the edge, and it acts as a controller manager for edge core resources. The second controller is called the device controller and is responsible for synchronizing device information between the core and the edge. It models devices with a device template and then creates device instances to store the actual configuration and the state of edge devices. The edge controller updates the instances in the cloud core with data that comes in from the edge. It's a lot of core and cloud and edge and stuff, but well, it is what it is. The edge core is a much more elaborate beast because it's designed for autonomy when disconnected from the cloud core. It too contains a hub device along with a service for managing containerized applications, service and event buses, a metadata manager, and a resource that represents in-cluster models of external devices. The hub handles synchronization of data between the edge core and the cloud core. It includes features for receiving, forwarding, verifying delivery, receiving responses, and then directing those responses to the origin device. It does this in both directions, with data that comes from a device, as well as with instructions that come from the cloud core and are going to devices. Devices themselves are modeled by the device twin component. It stores and syncs device status and provides a query interface for applications. The device twin component connects to the event bus, which is an MQTT client that offers pub/sub services to other components. Edge core also includes a service bus, which acts as an HTTP client and enables components to connect to HTTP services such as REST APIs for devices or other resources deployed within the Edge environment, but outside of the Edge core itself. The edged component manages pods on Edge nodes. It acts as the bridge that enables kube control commands to run against the cloud side to manage destination workloads at the edge side. And through the container runtime interface, it supports a wide variety of runtimes, including Docker, Containerd, and CRI-O. Finally, the Edge core runs the Meta Manager service, which bridges between edged and Edge Hub, and also stores persistent data in a SQLite database. KubeEdge is designed to behave as a single cluster with distributed nodes. The core Kubernetes functions reside in the cloud core. Operations are executed against the cloud core Kubernetes cluster, and these are passed to the Edge core locations as necessary. If circumstances require that the Edge environment be directly accessible, or if the Edge environment will spend more time disconnected from the cloud core than it spends connected to it, KubeEdge can also run full clusters at the Edge locations. This is called EdgeSite, and it replaces the cloud core functionality by connecting the Edge core directly to a local Kubernetes API server. EdgeSite includes an Edge controller, and because the API server is directly connected in the local environment, it removes the device controller and the hub components. KubeEdge might be the most familiar, but it's not the only infrastructure solution for connecting the edge to the cloud or the core. Alibaba created OpenYurt, and as one of my viewers said in a show last week, if it's from Alibaba, you know it's designed to run at scale in a massive way. OpenYurt follows a similar model to KubeEdge, except the edge nodes are full Kubernetes nodes that are converted into edge nodes using the yurt control command. The kubelet running on the edge nodes is reconfigured to connect to the Yurt Hub service, which in turn connects it back to the cloud Kubernetes cluster. Once wired together, the cloud runs controllers for nodes and also keeps an independent communication path over an encrypted tunnel. The roadmap says that they'll eventually have direct support for units, which sounds to me like they'll have direct support for interacting with the devices that are deployed at the edge locations. The use of a private, mutually encrypted channel for administrative communication allows the edge to run with restrictive network policies without interfering with the communication from the cloud server. This enables observability, interaction, and management without exposing ports to the internet. OpenYurt gives you a way to connect edge nodes to a cloud control plane and keep them autonomous when disconnected. It also has an uninstall feature, so your edge nodes can return to being standard Kubernetes clusters in the future without disrupting their operations. What it doesn't provide is any means for interacting with devices at the edge, but I don't necessarily think that it should. KubeEdge expects that you're running sensors and other devices that communicate over MQTT and HTTP. If you're not, and if you want more control over what you deploy and how it works, well then OpenYurt leaves your options open. Now, let's say that you've got some devices out there, maybe lots of devices. You're planning on moving to an immutable infrastructure model with no direct access, but you're not there yet. Some of your devices use dynamic IPs, and sometimes you need to reboot them or log into them. Maybe you want to run commands over SSH from a script, but you don't want to manage keys. Enter DevicePlane. This is an open source utility that you can even run in your own environment if you want to self-host it. Their cloud service offers 10 devices as part of their free plan, so you can also just take it for a spin before deciding what to do with it. In DevicePlane, you create a project, and then you click Register Device to register a device. You're given a custom command to run on the device, which installs a binary and then configures systemd to start it. The device then connects back to the core environment, shows up in the UI, and from there you can SSH to it or reboot it. And while those things are convenient, they're just the beginning. After installing the DevicePlane CLI, and setting your access keys and projects, you can SSH directly to devices from a local terminal. You can also view device resources, inspect individual resources, and generate reports in JSON. Device Plane includes an extensive IAM backend that includes service accounts for performing functions via automation systems like CI/CD pipelines, and multiple user roles for each project. Kubernetes clusters encrypt communication between control plane and worker nodes, or more specifically, between the services that run on those nodes. General communication between services running on nodes is not encrypted by default. So how do you go about encrypting node-to-node communication? WireGuard is showing up in more places after having been incorporated directly into the Linux kernel earlier this year, and Drago gives you a control plane that enables the configuration and deployment of overlay networks using WireGuard. It operates as a central server that holds the WireGuard configuration for clients. Those clients retrieve updates from the server on a periodic basis and apply the configuration changes to their local WireGuard instances. The server is designed to be flexible in how it operates, and it can store configuration in memory, in SQLite, or in one of various database backends. Agents on each node fetch the current configuration from the server's API, and then they perform reconciliation between the desired state and the actual state of the local WireGuard instance. Drago intentionally doesn't enforce a network topology. You're free to configure how and where hosts connect, and their UI helps visualize this while you're building the environment. For WireGuard-backed overlay networking with Kubernetes, you can use Kilo. This builds an encrypted Layer 3 mesh network that can connect disparate data centers and cloud environments, enabling true multi-cloud cluster operations or even cloud provider migrations of running clusters. Kilo also uses an agent on each node. This agent is responsible for the PKI infrastructure and the management of route tables for communication across the mesh. Now, it can operate as a complete CNI solution for Kubernetes or as an add-on to an existing Kubernetes cluster. When operating in add-on mode, it takes care of routing and encryption between the networks, and it leaves the local CNI to handle communication within the cluster itself. Kilo understands that different cluster configurations will have different networking needs, and it offers 3 topology types. In logical group mode, each group acts as a hub and spoke model, with hubs also acting as edge routers that connect to other hubs and their networks. Logical groups can be data centers, regions, VLANs, any group structure that fits your needs. In the full mesh mode, every node connects to every other node. And then there's a mixed mode, which is a hybrid configuration where, for example, nodes in one environment can form a full mesh, but then they can use one of those nodes as an edge peer to connect to nodes in a different environment that use the logical group topology. At the end of the day, this is WireGuard, so it can also act as a VPN server and give VPN users encrypted access to in-cluster resources, or even directly to the backend network where the cluster is running. VPN server nodes can also act as egress routers for the cluster, forcing all internet traffic to exit through a particular node. Kilo can also connect independent clusters over a WireGuard tunnel. One cluster could then access private resources in another cluster, either by direct IP, by a manually configured mirror service, or with automatic service mirroring happening with the developer's Service Reflector project. The Service Reflector provides an emitter and a reflector. The emitter is configured to announce services that the reflector then picks up and clones. A reflector can listen to multiple emitters, and each emitter can be configured to only announce services that match a particular selector. Let's flip this on its head and consider how networking will work between hundreds or thousands or even more devices. How many of you have built a network with that many devices that didn't rely on specialized hardware? What if you have to build a network of, say, 50,000 devices? How is it going to perform? What can you change to make it perform better? You can't just go out and do it. You can't even simulate it. What you need to do is emulate it. Bear with me for a second. Once upon a time, there was Mininet. Mininet performed network device emulation on a single node. Then someone created MaxiNet, which connects multiple Mininet nodes to enable emulation of larger networks. Each node in a MaxiNet network only handles a piece of the overall network, and emulated switches and hosts are connected via GRE tunnels. Control of the MaxiNet emulation takes place over API calls to the MaxiNet control plane. MuFog is a network generator that creates network and host environments that you can emulate with MaxiNet. It only generates the configuration, but it includes configuration parameters related to edge applications and their clients. MuFog works by using a generated network topology to create an undirected graph of network devices that are connected by links, with those links having a pre-configured latency and throughput. Networks are grouped into autonomous systems, and these are enhanced with fog nodes. Those fog nodes have a declared computational capacity, and the configuration specifies how many edge clients are expected for each application. This enhanced topology is then deployed into the MaxiNet emulation environment, and real-world applications are deployed as containers. This enables developers to run experiments that test their applications in real-world scenarios. From the generated data, they can make decisions about where application components should be placed based on how they perform. MuFog was the first place that I encountered the term fog computing. It seems that fog and edge computing are often used interchangeably if fog computing is used at all. But edge seems to favor the actual edge, whereas fog takes into consideration the area between the core and the edge. This could be as simple as the network providers and their links, or as complex as regional waypoints for data processing. Shadow also provides network emulation on a single host, and unlike EmuFog or MuFog, it has no external dependencies. It was originally built for testing Tor and Bitcoin-D, and it can emulate thousands of P2P nodes in a single host with full network topology configuration that governs the communication between those nodes. Experiments that run in the environment are reliable and repeatable, down to the emulation of CPU timing and network latency. The value proposition of Shadow is the same as MuFog, experimenting with how applications work in a real-world environment that is neither friendly nor controlled. Your development environment is a best-case scenario. Tools like Shadow and MuFog allow you to test what happens when latency goes up, when links drop, when a region goes dark, when nodes are disconnected, or really any other scenario that you can think of. Let's transition from infrastructure to applications. So I can't say edge without thinking resource constrained, and for many people, edge equates to single board computers like the Raspberry Pi. Honestly, the Pi 4 is hardly resource constrained with 4 cores and 8 gigabytes of RAM, but you're going to find lots of environments where running a complete OS or containers built from Ubuntu just isn't going to happen. So for those environments, there's Fly. At least one of you is watching this and you're thinking, okay, I don't have a wind farm or a fleet of driverless vehicles, I just want to deploy some apps. I understand. Fly is an application CDN with servers in 17 cities. You deploy apps using a local CLI, and they spin it up in the region closest to where the client requests are coming from on competitively priced VMs with features like shared and dedicated global IPv4 addresses, dedicated IPv6 addresses, and regional Redis nodes available for your apps to use for caching. Fly's objective is to get your application as close as possible to the person or device requesting it so that they have the fastest experience in interacting with it. Now, this is one of those services where it's easy to pigeonhole it and say like, oh, it's like Heroku, or it's like Cloudflare, or oh, you can only use it for static sites. Maybe, but no. If you check out their example apps, you'll see that they're really trying to make edge hosting useful, powerful, and flexible. They even have an example that walks through deploying the Kong API gateway connected to a Postgres database via an authenticated encrypted channel, routing to a backend service that may or may not also be on their network. With Fly, you can build powerful, connected applications and have them magically deployed where they'll run the fastest for your users without having to figure out all the infrastructure bits to make that happen. Do you know about unikernels? A unikernel is a specialized operating system that runs a single process. It's not a container. The containers share some similarities. Most unikernels are specialized for a high-level language, but the Nanos unikernel can run any ELF binary. This means that you can run anything written in a compiled language like C, C++, Go, or whatever the cool kids are using these days. And with ops, from the folks over at NanoVMs, you can also run apps written in PHP, Node, Ruby, Lua, or dare I even say it? Perl. I have to start by saying that Ops is in technical preview, so it might work, it might not work, it might steal your car, it might pivot overnight to sell t-shirts, but come on, how many of us are running non-production stuff in production? Ops is pretty amazing. So with Ops, you either run or load your code. Run is for bundling compiled code into the unikernel, and load is for adding interpreted code to it. Once built, the subsequent binary boots and runs almost instantly, and it has a reduced attack surface because it doesn't have anything else in it. Unikernels are machine images that can run in hypervisors, and Ops uses QEMU by default. Now, unikernels are also, they're super tiny, and you can run lots and lots of them on commodity hardware. Ops shows in their documentation that you can build and run unikernels pretty much anywhere, on bare metal with QEMU or in any public or private cloud. You can even run them in containers or on Kubernetes, although they say that doing so diminishes some of the security benefits. For one, you'll need nested virtualization, and nested virtualization means you're signing up for an immediate performance hit. So you could do it, but you probably don't want to. And then next up in the holy cow, this is super cool category of edge applications is NearDB. This is a solution that leverages the global distribution and uptime of S3 to create a database with blazing fast reads. It works with any S3 compatible object store, including Minio for on-prem environments. You can use it with existing edge solutions like Cloudflare Workers, Lambda at Edge, Vercel, or even Fly. S3 as an object store falls into the category of eventually consistent, and NearDB is not designed to be a solution for databases with lots of write activity. It's optimized for read queries, and when using a provider like AWS, it benefits from the CDN-like proximity of S3 nodes. It's also completely free and open source. Okay, let's rein ourselves back in from the CDN edge server application deployment model, and let's turn back to the idea of resource-constrained environments that need to do something. Everything can benefit from machine learning. If you look at every single process or decision tree that we follow, there will come a day when machines can do it better. We all know that ends with humans being destroyed by Skynet, but until then, there's a lot of good that we can do with it. Whenever I've taught people about shell scripting or automation frameworks, there's always a hurdle of, what do I use this for? And in those situations, I recommend that anything you've done more than twice is a candidate for automation. When I started looking into machine learning applications, I realized that they fit the same model. And like any linked series of discoveries, once I found the rope, I only had to follow it along for a short while before I found another candidate for ML, and then another, and then another, and then another, and so on. Take BerryNet, for example. This falls into the AIoT sector, and it uses one or more nodes to monitor direct or RTSP camera streams and do classification and identification of their contents. It works with multiple ML engines, and it can output to Telegram, email, and Line. All surveillance systems can detect motion, but it's hard to reduce false positives. Is it a person, a car, a bird? Maybe it's a spider that built a web across the camera lens because bugs respond to the IR flood the same as they do to normal light. Outside of security, there's a value in object classification in every manufacturing and distribution business. Think of anything and ignore the part of your brain that says, you can't use machine learning to do it better. If you think for a few seconds more, you'll start to have ideas about how you can use a machine to detect and classify a thing and then take action. For those of you with home automation systems, Frigate is another application that does real-time detection of objects in an RTSP stream. Now, this is designed specifically to work with Home Assistant, and it outputs detected object info to MQTT. I'm including it here because many of us have home labs that we use as test beds for projects that might not be part of our actual jobs. By building ML systems as part of an automation system that you use every single day, you can develop the skills and the muscle memory to take on new work and then possibly move into a different direction with your career. I'm pretty sure that this is supposed to be called microtensor, and it's just using U instead of mu. But if I'm wrong, you can just laugh at me for not saying U-tensor for the rest of this part. If all you need is a TensorFlow model built specifically for ARM and deployed at the edge, then take a look at microtensor. After training your model in TensorFlow, it creates a CPP and HPP file that you can compile and load into embedded systems. No fluff, just raw machine learning power. Because it's for embedded systems, they go to great lengths to guarantee resource utilization and heap allocation. They strive for the generated code to be readable and modifiable by a developer, so you're not looking at unparsable content when you need to go and troubleshoot something. I genuinely like seeing projects going in this direction, trying aggressively to be smaller and more efficient. I agree with Pete Warden's blog article from 2018, where he said, "I'm convinced that machine learning can run on tiny low-power chips, and that this combination will solve a massive number of problems we have no solutions for right now." Contrast this with other solutions that want $100,000 just to run an ML model with API access. That sort of approach helps them justify getting hundreds of millions of dollars in funding, but it doesn't help make machine learning available for everyone to learn, use, and benefit from. No matter where you work or what you're doing, you're interacting with edge computing in the world around you every moment of every single day. All of it is designed to do things better, but even edge computing isn't the end game. Something's going to come after it, and something after that, and something after that, as we push more processing power down to the place where it can do the most good, in the hands of real people. Thank you for joining me today. I hope to see you again soon.